and change the size of element. As Nikita says, for example, you are going from 1 millimeter to 0.5 millimeter, then you are going to 0.25, and you can continue reducing the size of element. And every time you have to look at the result and see if the convergence test is done. But you are going to make a decision about the size of element, and you are going to look at the trend. Although we have trend tracker tool, and we went through that one last time, then you don't have to create lots of a study, but you need to create one study, but you have to change manually the, for example, element size and run the simulation. And one issue here is we have 2 more tools in SolidWorks, which is, I'm not going to talk about it, what is the difference. The reality is not a big difference at this level of this course. You can go with both. Typically, we go with H adaptive. But what's happening in those adaptive meshing, as name says, instead of manually changing the value of the element, SolidWorks simulation is going to change the size of element automatically without your intervening, without your decision, such that you reach to some criteria. That is for case for H adaptive. For example, you say I want to have the maximum error, say 10%, 5%. It's going to run the simulation, make a decision about the size, and it's an automatic process. It's called H adaptive. And H adaptive, you're changing the size. SolidWorks simulation is going to change the size, but everything is automatically done. But you do not have any control on the process, and it's go through iteration, and it's limited to a static analysis. P adaptive is another adaptive meshing. SolidWorks simulation is going to adapt the size, appropriate size or type of elements. P adaptive is, this time, SolidWorks simulation is going to automatically make a decision about the type of elements. What we had first order, second order, and we said default is second order. And when you are running simulation and you are changing the size of mesh, you are not changing the type of mesh, you're just changing the size. P adaptive, on the other side, what we have P adaptive, and P adaptive is going to change the type of element instead of size of element. And you know that if when you go from first order to second order, you have more precise number because you have more degree of freedom, more nodes. Now it's SolidWorks simulation. If you say, okay, run for me the simulation, but based on P adaptive, then SolidWorks simulation is going to run the mesh adaptive convergence test based on changing the type of elements from second order to third order to fourth order, and that's a process. Is it clear? What is the P adaptive, H adaptive? For more information, my suggestion, look at the textbook anytime. If you have any question, let me know. But it's very clear that all you need to know is this is to approach, and there are some parameters, and parameters are well defined in your textbook. Any other question? Okay, it seems that there is no question, and we can move to chapter 4 and record the session. All right. Let's just move on to lecture. All right, let me just share the screen first. Okay, now let me share the screen. Did I share it? Let's see one more time. Okay, and let me, where is the record?
This meeting is being recorded.
Okay, now, as I mentioned, we are moving to chapter 4. And in chapter 4, we are going to deal with two issues. One, using SolidWorks simulation for truss structure and 1 degree of freedom beam element. Also, we are going to look at what is called direct stiffness method, which is a numerical, that's what we call it typically hand calculation, because you are supposed to do it by hand, but we are going to use software to do those kinds of calculation. Then there are two aspects to chapter 4. We have process structure and one directional beam element. And also we have direct stiffness method, which is the theory behind the software to solve the typical FEA problem. And let me just move on and show you what's happening here. See, if you remember from beginning, we said SolidWorks is offering different types of element in SolidWorks simulation. We have 3D elements, and we have beam elements, we have shell elements, and we have solid elements. Then the beam element itself, we can categorize it to truss element and beam element. I'm going to explain later on what is the difference between truss and beam, but for now, just if you look at this big table, which represents the type of element that we have in terms of 3D element, we have beam elements divided into truss and beam again. And in terms of the textbook, in chapter 4, our focus is on truss element. And in chapter 5, our focus will be on beam element. Right? Just make sure that what we are doing. We finished solid element, that was chapter 2 and 3. We are now talking about beam element, and we are going to focus on what is called truss elements and also one directional beam element, this area. And this is what we have in chapter 4. And when we finish that one, we are going to look at what is called beam element, and it's chapter 5. Although you see beam, don't just make sure that you know what's going on here. The reason this is a little bit confusing here is we see it is because truss is a subset of a beam anyhow. Because what we really have here is we have beam element and truss is a subset. However, because of the definition of beam and definition of truss, then SolidWorks is going to provide that option that you can have either truss or general case of beam. That's why we have beam here, beam element, and again we have beam element here, and we have truss. I didn't move those here, first column, because this is what we have. And from my perspective, it makes sense, and you can realize quickly that yes, it has to be categorized this way because truss element is a subset of the beam elements and the beam elements in general. And that would be the focus of our lecture today, beam truss element. Now, before moving forward, let's talk about a couple of issues here. Generally speaking, there are several methods to formulate the finite element problem. And what I'm saying here is finite element problem, finite element analysis is a numerical approach. And what we are doing in terms of solving those, in terms of using numerical approach, we may have different methods to use in order to use a numerical approach or a numerical method. And there are different ways in mathematical, there are different types of mathematical approach to solve finite element problems. And 3 well-known approaches are called direct method, variational methods, and weighted residual methods, or Garkin's method. Those are 3 different approaches. The first one, direct method, is based on fundamentally is based on equilibrium equation at element level, at when you write down equilibrium equation for element at each node of element, then that is what is called direct method, because what we are doing here, we are going to look at the equation, displacement equation and force balance equation directly at node level in our analysis. That is one approach. Another approach is what is called potential energy approach. In potential energy approach, we know that if there are loads applied to a structure, for example, and what will be the result if you apply forces and torques and moment to a structure? The result, assuming that you are below the yield strength, then the result is you can see the deflection. You apply the load and there will be deflection in the structure. And then what's happening here is there is an energy, change of energy here. You are applying force that creates the displacement or deflection in the structure. And that force multiplied to that deflection creates work, and work is going to be saved inside the structure like energy. Then what you have here, you have two types of energy. You're applying the force as a work, and you can save the force inside the structure as a deflection. And we call that one potential energy approach. That's another approach. Again, don't forget, we are not talking completely about two different problems. Our problem is FEA. The method that we are going to use to solve FEA problem is different. And this is just only three. It's not limited to three, but those are most commonly used three approach in FEA. And finally, we have weighted residual methods that I'm not going to talk about that one. Look at the textbook. There are some explanation for that one. What we have here in this course, we are going to look at direct method, the first one. It also is called a stiffness method, direct stiffness method, or DSM. Okay, this is what we have in chapter 4. Direct stiffness method is the method that we are going to use to solve finite element problem. Now, in chapter 2 and 3, when we talked about solid element, we never talked about those kinds of equations. If you remember, I always said what you really have here is you have just a bunch of equation behind the scene, and by defining the geometry and boundary conditions such as force, fixture, material, and those kinds of parameter, you are going to define a mathematical representation of your problem. If you remember that, now what we are going to do, we are going to look at a little bit a simple case in terms of loading and structure, which is beam and truss, and we are going to look at those equations. Then you can really see what is FEA. When we say SolidWorks simulation is going to solve the problem and give you the result, what are those equations and how SolidWorks is going to solve them, or any CAD package. That's why we didn't talk about those methods in the beginning. We talked about solid element to get familiar with the application of the tool, get familiar with solid elements and post-processing, pre-processing. Now you have a good solid understanding from FEA. Now we are going to look at how directed stiffness method works in order to give you those results. All right, FEA direct method, I think I talked about this one. I said we are going to look at this one. There are two approaches. We have force method and displacement method. In this course, we are going to look at displacement method. Quickly, you realize why we call it displacement method. However, this slide is available in the course homepage. You can look at more details if you want. Let's look at what's happening here. What I have in the next couple of pages, slides, I have a bunch of equations. Don't worry about them. We are going to create those equations with MATLAB. and you don't have to worry about those equations, but try to follow me in terms of procedure, what's happening here. Remember we said when you want to deal with FEA, you're going to discretize the model and you're going to select the type of elements. This is the first thing that you're going to do. Now, in numerical approach, what we are going to do, we are going to make a decision about type of elements, and then we are going to select what is called a displacement function. And that displacement function is within each element. For example, we have the deflection is, say, we are going to look at the second order displacement function. And we say that I can model the displacement as a second order. All right, this is what you're going to do. Then you are going to define the strain and a displacement relationship, or a strain stress relationship. And you know that relationship, yeah? The relationship between a strain and displacement, or if you look at it from a different perspective, you can say it's a Hooke's law. In Hooke's law, what you have sigma equals E modulo of elasticity times strain. For one directional, you have sigma x, you have epsilon x. In general, you have different types of strain, then you have different types of sigma. Let's focus on one-dimensional elements for now. Then what's happening here is, at this step, you're going to write down the strain equation based on the displacement, or you're going to write down the displacement equation. That's why we call that one directed stiffness method. You are going to start from displacement, not from force and force balance at element level. Then we are going to find, again, the terminology that I want you all to keep in your mind is this. We are going to write down element stiffness metrics. This is the first time we are talking about the stiffness metrics. If you remember from physics in high school, we had always, if there is a spring, you are going to apply, and you're going to apply a force. Always you say what? If there is a spring, I'm going to apply F force from both sides, and say there is a displacement. Say after applying force, we have X, which represents getting shorter. Yeah, if you apply force, it's going to compress and it's getting shorter. Then you have delta X representing the displacement. Then F divided by delta X for linear spring is called K, and we call that one a stiffness. That K is called a stiffness. And if you look at this equation, we have F equals K times D, and D is displacement. Now, this equation, which is the first simple scenario in terms of geometry and loading, which is one directional only for a spring, it looks same in terms of the component. We have force, we have displacement, and we have K. However, if you look at this equation, I put some bracket over those parameters, because what we are doing in finite element analysis, we do not have only one node or one element. You know that if you discretize the model, you will end up with, say, 100, 1,000, and those kinds of numbers in terms of the nodes and elements. Then what you are supposed to have, you are supposed to have a vector of element, what is called nodal force. This is what we have here. We have the force displacement equation at element size. This is the force displacement equation, but we are going to write down this one for at element level. Then what you will get here, you get the first vector is called element nodal forces. All the forces is going to apply to those nodes. This is one node, this is another node for one directional spring. Then that represents your nodal forces. Then here you have displacement for each node. You have D1, D2. For example, in this case, only we have D1 and D2. If you have lots of those springs connected together, then you may have D3, D4, and so on. Then that represents a nodal displacement. It's a vector now. It's like a matrix, yeah, but it has one column and it has n row. And now, in order to multiply these together, you have what is called element stiffness matrix, which we call it K, and you know those numbers now. K11, K12, all the way to K1n, and you have Kn1 all the way to Knm, which means that your stiffness matrix is n by m. All right. Now, if you look at here, sorry, n by n is the square. If you look at here, you can, next step is, you are going to say, okay, that represents each element, yeah? What about in the entire part? Because in FEA, we are going to discretize the model, but we want to get the result for entire part. We don't want to just get result for each of those nodes. This is what's happening, what we call, we are going to assemble the element equation to obtain the what is called global equation, or global force displacement equation, which is in this case what you have. Again, same format, F equals K times E. This is the only equation that we need. All we need to know is just try to make those matrices and plug them in this equation. Now, what you have here, you have capital F, capital K, and D. I didn't use capital D here because capital D, we are going to use it later on for different terminology. Now, what's happening here is those F represents global nodal forces. That represents a global stiffness matrix, and that represents the global displacement vector. Now, here what's happening is this one depends on how many nodes and how many elements you have in entire part. That one was just for one element. That's why we use the terminology here, assemble. Right? And we are going to solve this problem depending on what is the unknown. Some cases you are looking for reaction forces unknown. In some cases you are looking for displacement of a point of interest. Depending on what is unknown, you are going to find it. However, K is not unknown in our course. K is, it has to be calculated. The K, that which represents global stiffness matrix, you need to calculate this K. At both level, you need to calculate at element level, and you need to calculate that one at global level. Then this is our job to calculate this one. D1 all the way to Dn, it's a boundary condition that you are going to find from the problem. In some cases, those are known. Some cases, those are unknown. On the other side, on the left side of this equation, what we have forces. Those can be applied forces, which are known, or those can be reaction forces, which maybe we don't know them. Then what's happening in this equation, very interesting equation from metrics perspective. This is known. Here you have some unknowns. Here you have some unknowns. Don't forget, if you remember from the tutorial that we had for MATLAB, we said you can write the equation in the matrix format, and MATLAB is going to solve the problem for you. Then our job is to create this equation. Our job is not to solve this equation. It's just a couple of line code. Remember, we had a linear algebraic equation in chapter 1, and one of the tutorial that we had a set of algebraic equation. We use MATLAB to solve those set of algebraic equation, linear algebraic equation. Same goes here. Those are numbered by the end of the day. Those are, some of them are number, some of them are unknown. Same goes on the other side. Then what you really have here is a set of linear algebraic equation. Then our job is to just create this matrix and then MATLAB is going to solve. There is no way, if you, for the simple case we are going to solve it, you can see it. You can see that how we can solve this kinds of equation. But when it goes very, very complicated in terms of size, there is no way you can do hand calculation. You have to use software like MATLAB. All right, and finally, I think when you solve those, if there are sometimes there are some calculation or some sort of post-processing in terms of the magnitude of stress and strain, depending on what you're looking for. And finally, we have interpretation, post-processing. You need to interpret the result. Now, what I want to say here is, I'm 100% sure for most of you, you got lost. What's going on here today? We are supposed to see SolidWorks. We are supposed to be part, forces applied, run the simulation. Your expectation was to see such an environment. But what you see here, you see lots of equation. And now you may ask question, what we are doing here? And what is the objective? The objective is, one more time, I mentioned in the beginning, I'm going to repeat what I said. The objective is to look at the theory behind the SolidWorks, the way that SolidWorks is going to solve those equations. And we are going to do that for beam structure and truss structure. This is what we are going to do. And in order to do that, we are going to use matrix algebra that we learn to create those equations that we don't see in SolidWorks simulation. All we see is we see that SolidWorks is running and is going to give us some numbers. What's going on in that solving process that we don't see, that's the objective of this lecture. And let me just show you here. And the reason we are covering this material is for two reasons. That's a key issue to keep in your mind. One issue is to teach FEA, because when we say be careful about boundary condition, when we say SolidWorks is, remember I said you may end up with a problem, and SolidWorks simulation is going to solve that problem. But I clearly mentioned that maybe it's going to solve a problem which is different from your real life problem, because SolidWorks don't see your project. SolidWorks see what you enter to the SolidWorks. SolidWorks is going to define its own mathematical representation. Now, and this is the key issue in simulation. And now you should see how SolidWorks sees your problem. And the only way that you can see that one is if you write down the equation by yourself. And now you can see the connection between the theory behind the scene and those boundary conditions that you are going to apply in SolidWorks. Now you can see when you say fixed geometry, what does it mean from mathematical modeling representation in SolidWorks? That is one objective. The second objective is, if you remember, I talked about design verification and design validation. Design verification or FEA verification, I think the better is better to use FEA verification and FEA validation. What was the difference? The difference was in validation, you need to have a physical test in order to validate your FEA model. That was the meaning of physical validation, in terms meaning of validation. You need to have a physical test. You need to have a part, you need to apply force, you need to use strain gauges to measure, for example, the strain and stress and compare with your result, right? Which is not all, that one is not always possible because it needs to have some sort of physical setup. But that's the best if you can end up with some sort of physical setup to make sure that you can rely on your simulation result. because when you get the result from physical tests, then you can say, okay, my model is correct. Then you can work on what if scenarios in your model. Then you do not have to create more physical model. One is good enough to validate your model, but that is the best. The reality is sometimes that's not the case. Then you need to at least verify your result. And what was the verification? Verification was, if you back to chapter 2 in terms of the definition and a couple of my slides, verification is the process that you are going to verify your FEA model in SolidWorks simulation by some another mathematical model. Then what you did in FEA SolidWorks simulation, or you are doing in FEA simulation, you're going to create a physical model. Sorry, you're going to create a CAD model. You're going to apply boundary conditions such as forces, fixtures, and so on. And you are running the simulation. Yeah, that is, from your perspective, that is the model. From SolidWorks, that's a mathematical model. Now, you should end up with another mathematical model, another tool to make sure that your model is correct. At least you can verify your model with another tool. And this is what we call verification. Now, having said that, this approach is good, because if you look at here, we are not messing up with SolidWorks simulation. What we have here, we have math. We have a governing equation for our physics, for our problem, for our project. Then you are going to solve the problem for given project using another completely approach, which is mathematical model. Now, the result from this approach, which has nothing to do with SolidWorks simulation, should match the result of your SolidWorks simulation, because this is verification. This is a mathematical model. SolidWorks simulation was, by the end of the day, a mathematical model. And that is the second objective of this directed stiffness method. I hope it's clear, and we are going to look at it, how we are going to do it in next hour, but I'm just want to make sure that everybody is clear from what is the procedure and what is the application and how we can do it. It's something that we need to do a little bit coding, which is next hour. Let me stop recording, and I'm back to the chat area in case you have any question.
The recording has stopped.
All right. I talked a lot, yeah. Any question about material that I covered before going to a break? Talking and 10 minutes break. We have 58 students. It means that in my lecture now I have whole class, and there is no question. Come on. Remember, I think one of my lab, I'm doing some sort of, I have a small shop in my office as well. And what I did, I started using my handsaw, and I forgot to, I forgot to mute my microphone, and it was a torture for the rest of the student. And they said, what happened? I said, sorry about that. And the reason was, you guys don't ask any question, then I have to use my handsaw and cut metal. It makes lots of noise. And if you guys don't ask any question, I'm going to use my handsaw one more time and create problem noise. No question? Okay. If you don't have any question, I don't want to start the next topic because I don't want to stop in the middle of those equations. Then let's have 10 minutes break, and we are going to start at. Oh, Nikita said we are absorbing information. Yeah, I agree. I agree. This one is a bit. You need to absorb. It's too much to digest in one session, and that's why that direct stiffness method and that equation and coding, we have at least that one for next, I think, 4 weeks. And you are using SolidWorks simulation as well, but we have coding and those equation, and hopefully by end of next, I think next week, you will be well familiar with direct stiffness method. DSM is something that using MATLAB is much easier, and it is an interesting topic. This method uses a stiffness. Okay, there is one question from you. This method uses a stiffness and displacement in metrics to find force, right? Yes, yes. Are we going to use FEM in MATLAB? Yeah. What we are going to do, we are going to write the code in MATLAB, but we are doing FEM or FEA in MATLAB, but we are going to use MATLAB in terms of coding environment. And MATLAB is not going to do some sort of simulation for FEA, just using coding environment. Any other question? All right. Is there a benefit to using this method than other two? I'm not clear what is the meaning of other two. I'm not clear on this. When you say other two, what method you are talking about? This is direct stiffness. Oh, okay, good question. I think you are talking about, sorry. Yeah, I think his point is comparing to, yes, variational method and weighted residual methods. My suggestion is, Jay, you look at my my book, and there is one page I explained what is the application of those. I see you're comparing direct stiffness method with, for example, potential energy approach and the Gardekin approach. Yeah, please look at quickly on that page, which is the beginning of chapter 4. If you still have questions, let me know. Yeah. All right, let's have a break and see you guys in 10 minutes.